Okay, so I think we can start, and well, other participants will join as soon as they can. Okay, so once again, welcome everyone to this last webinar. Well, actually, this is a roundtable, so we will summarize a little bit what we have done in the previous lessons. And of course, we have special guests also today, Professor Restrepo, Professor Conte. So if you have any questions about the model, about the theoretical background, we will try to answer questions. Okay, so we'll share my screen, and I will start by summarizing what we have done. Okay, I go on the other computer. Okay. So what we have seen in the first lesson, it was how to use shell element, okay, with a three-dimensional constitutive model. And actually, in the first webinar, it was a two-dimensional constitutive model. Let me just reopen it. So if we go back to the first one, shell smeared. Okay, so it was a shell element, but the material model was the material model that I was using was the material model from Professor Yuxin Zhang. It is a tensorial constitutive model, but it is only plane stress. So it cannot represent the out-of-plane behavior. So in order to do so, I show you how you can use the plate from plane stress, but then the out-of-plane modulus, so the out-of-plane shear, will be elastic. Now, it is not a huge problem for thin walls. Okay, but if you need to model a nonlinear out-of-plane shear, like imagine you want to model punching shear in the out-of-plane direction, then you need a three-dimensional model. In this example, I've been using the plane stress user material. You can use any other three-dimensional model. In fact, in the following lesson, we have seen the three-dimensional model and how you can use the damage TC3D, but you can use it also in the shell element. Okay. Now, regardless from the three-dimensional model, what you have seen also is the concept of smeared reinforcement. Okay, so if you see here, this is just a surface model. The rebars are not modeled explicitly. Instead, you have a one-dimensional model for rebars. It is converted into a plate material with the plate rebar wrapper. It basically takes the original material, takes an angle of orientation, and it converts this uniaxial material into a plane stress one. Okay, so that you can put it inside a layer shell. Now, I call this one smeared because actually the rebar is not at a physical location. It's just smeared everywhere in such a way that the overall area, the overall amount of steel is the same as in the physical model, but it is not actually the same. Then in the second lesson, we have seen how to use solid elements, but it was not actually focusing on solid modeling itself, but how to use embedded rebars. Okay, because for example, in solid element, you cannot use the concept of smearing the rebars with the plate rebar, because this is done for shells. Instead, with the solid, one option that you have, if you need to do detailed solid modeling, is to use the embedded approach. So just to explain you what it is, just a brief recap. If you have a three-dimensional model and you want to include rebars, what you can do is to draw the solid model, then the rebars in the middle. So if I switch off the solid, you will see that there are physically the rebars are as beam elements inside. And then you need a particular boundary condition to embed them inside the solid domain. Okay. Now this can be done also for shells. Now in this case, I just shown how to do it with solid elements. Then in the third, so let's say these are generic three-dimensional models. Then we have what also Professor Restrepo called phenomenological models. So they are more performant, but more targeted to a certain kind of problems. And we have seen the cyclic truss model, which is the two-dimensional version of what they also developed and extended as a three-dimensional beam truss model. I told you that now we only support the truss model, so for the two-dimensional model, but soon we will also implement an interface for the beam truss model. Okay, so basically, let me open it. So let's go to there. truss model. Okay, when you model it, basically it's always a surface inside STKO, but then the output, as if you remember, is the assembly of trusses, as we have seen in the, let me open this one. Is an assembly of trusses, okay? And we are planning also to improve the post-processor of this one. And then we have seen how to use also the multiple vertical align elements, okay? So the last approach that we have seen, just to show you what it is, it was this one. So the fourth one, shear flexion interaction, multiple vertical line elements. Okay, so once again you draw it as a shell element, then they are discretized as basically pieces of beam elements that can incorporate somehow. Oh, here we have also Professor Spacone, which is joining, which is basically a sort of beam element with a geometry of a shell, and it can handle this sort of shear flexion interaction. Okay. Now, before starting all the questions, I wanted to make a couple of points, a couple of ideas. So the first one is that when it comes to model this kind of problems, but this is actually general, there is not a unique modeling approach that can work for every kind of scenario. Okay, so each kind of modeling approach has its own drawbacks and pros and cons. So basically, none of them is perfect. And then there is another problem. Whenever you try to model strain softening, so you have problems like when you have concrete or masonry. So whenever you have a material that shows degrading response, it is very problematic to model this with finite elements. You have a lot of problems. So I've been talking about the concept of fracture energy regularization, which is a sort of a first attempt to try to regularize the response, but also that one is not perfect. So the first rule is that you have to pay a lot of attention. You cannot just think that one model can work right away, okay? So one thing that we have seen, so I will start with showing a couple of issues that you may encounter. So we have seen, for example, using the shell approach. If I open one of the outputs, so the first thing that I want to explain now is one error that you may see if you use the smearing of the rebars and you have strain softening like reinforced concrete. This is one problem that may happen. It may happen that let me go back here in round table, shell smear course. Now imagine you do this kind of model and you use a coarse mesh. Now in this case, the mesh is exactly the size of the spacing between the web rebars. Okay, so in this case, it was 180 millimeters. So the material properties are the same as the last time. So if I try to visualize the crack pattern, which was already visible there, but I want to show the crack here. The maximum membrane deformation. So you see here a nice diagonal crack appearing. Then what may happen, and then the same thing was happening with the truss model, for example. Okay, so if I open, not this one, sorry. If I open the Cyclic truss model, regular 180, you see a very nice diagonal crack here. Okay. Now, something that you know from finite element is that as you refine the mesh, the solution will converge to a better solution. This is true if you don't have strain softening. If you have strain softening, this is not true anymore. You have to pay attention. Now, fracture energy regularization is a way to make sure that the total dissipated energy is the same. But actually, the fracture energy regularization was a very rough method that works perfectly for a constant state of stress. But when you have bending and shear, this is not perfect anymore because you have something called size effects. Okay. So in this case, for example, a microstructure has a physical size, which is actually the spacing between the rebars. Okay, the rebars are not so small, so you have a physical size that can represent the behavior here. So if you try to refine the mesh of this model, so either with the CTM, with the cyclic truss model, or with the shell model, with the smear rebars, you will see a slight difference. So for example, we have seen it with the truss model last time, but you will see that it happens the same with continuum models. Let me open the round table, smeared fine. You will see a difference. Okay. So if I go here, at the end, still I have pretty much the same behavior, but you will see that now the diagonal track is not so well defined here. I can have a more bending. I have this crack at the bottom. Let me show the maximum principal deformation, so they are more visible. So now what happens is that you see this first crack opening at the beginning, and then you have this more curved crack. Okay, so it's not starting actually in the middle. So you may see something like this. Now, this is not the only example where this can happen. It happens every time you have the mesh which is finer than the microstructure. This is pretty much the same problem that happens with beam column elements when you have the finite element size which is smaller than the plastic hinge length. Okay, so the solution is not exactly the same. So this is one of the first problems that you may encounter with strain softening, which is the size effect. So you either model the microstructure, as I've shown, for example, modeling the rebars physically and using the embedded condition, but then the model becomes very complicated. Or if you want to use a smeared approach, my suggestion would be to have a mesh size which is comparable with the microstructure. Okay, pretty much the size of the microstructure. Now I don't know, Professor Restrepo, if you encountered this kind of problem also. I know that you mentioned last time that the angle, so basically the element distortion, in your model should have some equation, but I think they are related to the geometric position of the rebars. Is it right?
No, it's mainly related to the state of the stresses. So before the structure cracks, also. So because we are not rotating anything or so you better start with a good idea where should the cracks begin to develop, and an idea is that you could eventually start with a linear finite element also analysis.
Okay. And did you experience some kind of behavior like this, for example, when you refine a lot the mesh?
No. In fact, we have never refined the mesh that way, so I cannot tell you. The idea to start with is to have more of a macro approach as opposed to a micro approach. So
exactly. So basically,
I did have some comments to Lin soon about going very small in the meshing, because you're getting very close now. You are assuming the concrete to be a homogeneous material, but in the end, if you go very small, there is the problem of homogeneity. It goes away, and now you have to think about other things. Exactly.
So this is just to explain. So for the participants that are not familiar with all the concept of strain softening, is that one important thing is the size effect. So we always assume that a material is homogeneous because when we look at it from a macroscopic point of view, let's say from a structural point of view, we can say, okay, a wall is much larger than the microscopic structure of the reinforced concrete, which can be related to the size aggregate, or in this case also to the spacing of the rebars. But the problem is that the wall can be as large as you want, but the problem is that whenever you have a strain localization, the real size of the problem is not anymore the structure itself, because when the strain localizes inside a finite element, then this one becomes the size of your problem, and this one in this case is smaller than the microstructure. So the problem is that you will never converge to an exact solution. So just to explain, for example, this problem in the case of smeared rebars. Let me see if I can annotate something. So when we talk about smeared rebars, what we do basically, imagine in reality we have, but this is true for any kind of microstructure. So I will talk about the rebars, but this is the same for any kind of microstructure. So in reality, let's say we have a representative volume of concrete, and here we have a couple of rebars with a certain spacing, okay? So now if we have a finite element which is pretty much the same size of the spacing here, so I will have a finite element like this, and then at their integration point, I have a material model which has a percentage of steel, which is pretty much equal to the area of this one. So it still makes the problem pretty similar to the microstructure, but so it is equivalent to basically a rebar here and another rebar here. Now, when you keep on refining the mesh, imagine I start having a very, very fine mesh like this. Now, each one of my finite element here, at its integration point, they will have another contribution of steel with a smaller area, but this one will be basically equivalent at having a lot of rebars, like this one, many rebars, with a very tiny area. So as you keep on refining the mesh, you tend to an homogeneous material, but actually in reality, the material is not homogeneous. So this is one of the problems that you have with strain softening. In general, in finite element, you try to refine the mesh as much as you can to reach convergence. When you have softening, don't expect from this mesh refinement a convergence to an exact solution, because this is not true in any case, okay? Not in every case. You should pay attention.
Massimo, I have a question for you about this. So if you, I think you are talking about when you model the reinforcement in a smeared fashion, right? If you model the reinforcement as embedded, you know, with the real dimension, the distance between the rebars and so on, does what you said still applies as you refine the mesh for the concrete more and more, or this problem does not?
Yeah, partially, because for example, in reinforced concrete, the microstructure is given by the reinforcement, but also by the size aggregate. So basically, if you have a finite element which is of the order of millimeters, they are smaller than the aggregate size in the reinforced concrete. So yes, if you place the rebars physically, you improve something, but you're not going to solve everything. So the point is that, well, many times actually you don't need to do such a refinement because you want to use performant meshes. So you may want a coarser mesh. Okay, this is just to say for people that has the assumption that in finite element, as you refine the mesh, you go to a unique solution. Just to keep in mind that this is not true whenever you have softening. Okay. For example, when I was doing my PhD, I was working in masonry. There, the microstructure is even more important because it's much larger. And when you model the microstructure, it was very easy for the crack in masonry to develop, okay? And it gave a very nice prediction. The problem is that if you do an homogenization of this, and you use a very fine mesh, which is much smaller than the brick, the crack prediction will be linear. So the crack will be, even if the equivalent homogeneous strength is the same, and the amount of dissipated energy is the same, the crack will develop much faster because the mesh itself is more able to bend than in reality, okay? So I don't know if it is clear, this concept, but you make everything more homogeneous than it is in reality. Okay.
Let me make some comments, Massimo. There are bad news and good news. The bad news is that this wall that you are presenting here, it's one wall that has very light transverse reinforcement, very, very light. And the bad news is that those structures do exist. Okay, so they were built in the 1950s, 1960s, and now there is a need to retrofit these structures. So the assessment of these type of walls is important and is challenging. Yeah, those are the bad news. The good news is that as soon as you have a little bit more of transverse reinforcement, even though the wall will end up failing in shear, it becomes less, and the prediction becomes less uncertain. It's easier to work. This one is particularly challenging.
Yeah.
But I have a question for you. Like, do you think the boundary conditions experimental of these tests are realistic? Because this is just one floor that behaves like a cantilever. So it means that could be only a building of one floor to represent this kind of behavior. And it's not really realistic. There's a thing like there are no buildings that are built like that.
Oh, there are buildings that are, no. There are buildings that are built like that when you transition, for example, from a tower into a podium and you have side walls, because you're going to have retaining walls. So these are not an
retaining wall. Okay.
Yeah.
So it's the retaining wall.
Yeah, close to, they begin to have retaining wall down the surface. So maybe above ground, but you still have a podium, and then you're going to have a tower. These walls do exist, and they are challenging. But as you say, this is a challenging exercise. So it is an exercise that is going to really exercise any of the modeling techniques. As soon as the transfer reinforcement increases, say by 50% or more, it becomes easier to predict.
Yeah, actually,
even if it's going to fail in shear.
I didn't think about playing with the amount of reinforcement. Yeah, I could have done it. But actually, in fact, at least in my experience, what I've seen is that for this kind of boundary condition, just to tell people that this is very challenging. What I've seen, for example, if you have a slant in this case, you have a beam, a wall loading as a cantilever. So this is free to rotate, free to uplift, but it is very small. So basically, if you have a slender wall like this, it is not a problem. It will fail in shear, so it will be captured very well, even by beam elements. So you don't need to go in with the complex models. Then I've seen that with squat walls, if you have some sort of retaining against the rotation, like a shear kind of motion, it is not a problem because shear will prevail. But in this case, when you have this kind, and then I didn't think about the reinforcement actually. But in this case, when you have a cantilever kind of load and a very squat wall, it is really a mess because the shear and flexure interaction, it's quite hard to capture.
Right.
Then I didn't think about also the light reinforcement, which in this case makes the problem even more unstable. But yes, so just to tell people that are approaching to this kind of model, probably my mistake was to use the most challenging example. I should have used something a little bit easier. But yes.
Now, where do we find also this type of walls? In industrial facilities, power plants or so, they're comprised of many complex low rise, high rise walls, and you always need, so they're not necessarily a building thing. They also tie them in the old piers of bridges that instead of columns had walls and they were lightly reinforced. So we have a few of those in California as well. So they're not the bread and butter, but they are not uncommon either.
It is important to find a way to capture their behavior.
Yeah,
Massimo, another question. Can you comment on so the shell, modeling approach? I mean, on the surface, from a high level, right? It's more physics based, more fundamental, so to speak, is the beam truss model. Now, what about the beam truss model? Everything is uniaxial, right? So the stress strain constitutive model are uniaxial. It's very easy when you are uniaxial to go and put many type of phenomena in the constitutive model.
Actually,
for the multi-axial constitutive model, it's much more difficult to
in fact, it was the second point.
So the question is, if somebody would put a lot of effort to refine the constitutive model multi-axial and to put all these ingredients that are easy to put in a uniaxial, do you think that the shell approach for this very challenging problem would would work as well as the beam truss model.
I think, but I mean, I think actually we are thinking of improving the three-dimensional model, because actually I've seen many nice behaviors shown by the beam truss model. So I wanted to try to incorporate them into a three-dimensional model, because actually, yes, the beam truss model is made of, correct me if I'm wrong, Professor, it's made of trusses, so uniaxial materials, but there is a bidimensional effect in the sense that the particular truss element they use.
Yes, it has a dummy strain gauge, and the dummy, the stress strain of the diagonals, the stress strain relationship of the diagonals is coupled to the transverse strain, as is in the diagonal compression field theory of Frank, Vecchio, and Collins.
So what I've seen, for example, is that imagine the diagonal that you see here is actually in OpenSees is actually made of 4 nodes. So you have the 2 nodes that define the axial component, and then you have the other 2 nodes, and based on the angle, now I don't remember exactly, but somehow with them you obtain the transverse deformation, and with this transverse deformation you actually change the behavior of this one.
The constitutive stress-strain relationship in compression, yes.
So what I remember is that here you assign, but in each one of them you assign a uniaxial material with only compression, no tension. But then, I mean, there are 2 of them, so it's basically like a shear response here. And then how strong they are, it depends on the transverse deformation. So they do have a coupling with.
Yes, absolutely. Not only the strain, but also the entire relationship depends on the transverse strain.
Exactly. What I remember is that if I'm correct, the user defines the reference value. So basically the value that you have if you don't have transverse strain, right? So the transverse strain is 0. And then you have a relationship here which goes from 1 to a residual plateau, and this one was a beta factor, so let's say a scaling factor, and this one is the transfer deformation.
Right.
So it goes either from 1 to a plateau value, a residual value. So basically,
yeah, that's no different from what Frank Vecchio proposed in his modified compression field theory.
Okay. And then I didn't read about it, but do you manage to have like an increase in biaxial compression? Because what we have, for example, in the three-dimensional model is that, well, the typical surface is something like this.
Yes.
So this one is the compressive strength. Now, if you load it in biaxial compression, you have a certain increase here. But actually, I've seen that if you don't have too much vertical compression, it is not important.
The effects of confinement are explicit. They don't change during the analysis. You calculate if you're going to have a triaxial, no biaxial, triaxial stress state like the boundary elements. You explicitly calculate the effect of the confinement on the 1D stress-strain relationship, and that enters. But that does not change during the analysis. It's
so
defined.
For the user, exactly. For the user, if you want, for example, if you want to model the boundary beams, in my case, I did it with beam elements, but if you want to do them with the beam truss element, you should take into account the confinement before
Yes.
you define a modified constitutive model.
Yeah.
Right?
Yeah.
Which is basically actually what we do in beam elements.
But that's typically done for the vertical elements, not for the diagonals. So the diagonals are considered to be unconfined, and they will only go down in the strength as your strain field transverse to the element increases in tension.
Yeah. And then oh, perfect. And then another couple of things that Lin Sun was working a lot with this model, try to understand how do they work. So let's say basically, if you want to use a general model, you may want to go with a three-dimensional tensorial model because it is general. But sometimes they can have some issues because programming them is a little bit more challenging. For example, one thing that we cannot do with that, which in this case, it's very important actually, it's the hysteresis loop. So with three-dimensional model, basically the most that we can do, now I represent it as a 1D model, but basically, if I do a cyclic test like in tension, okay, then I want to consider a certain plastic deformation like this. When I go in compression, I will start from this point, so that the permanent deformation will never be recovered completely. Then when I go in compression, let's say I have a certain unloading stiffness, which is not exactly the initial one, can have a certain amount of damage, but when I'm here, I will reload in tension at this place, okay? Now, this seems not important, but actually, if you have a lot of cycle, it can create issues. I'm referring to Lin Sun. You remember your test that you have done cyclically with the three-dimensional model. You may obtain something like this. Let's say the backbone is this one. Okay. Now you start doing cycles. You do something like this. The first one is good. Then here you do not recover. So when you go and let's say the negative backbone is this one. Here, this one is the point where you will start softening on the other direction. If you do not fully recover this, I reach here and I will start damaging at this point, not at this point, okay? So you will see a certain first cyclic damage, let's call it like this.
A shift, yes, a shift in the relationship, yes.
In the global response, if you have a lot of cycles, this looks like, it makes actually the structure more brittle, because actually when I'm here, for example, then my next plateau for starting softening on the other side is this one. And in the experiment, I want to try to push it up to this point, but my wall will start failing here because it is hitting the surface at this point. And so when I reach this point here, it will go already in softening. Instead, with the beam truss model, what happens is that when I go here, I have a certain pinching effect and I start reloading here. And so here, I will hit my, let's say, yield surface or yield limit, and then I will start going back. So this one seems not important, but when you have a lot of cycle, it is very important, because at the end of the day, what will happen with three-dimensional model, if you expect a backbone like this, if you do a monotonic test, is fine. If you do cyclic, you will see something like this.
That pinching is very typical of concrete. The shift that you show initially, it's more like reinforcing steel as a material. When you experience that shift, but as a 1D relationship in concrete, you will have that pinching before the crack closes, you regain stiffness, and then you go and merge. Depending, some models will have some damage, and then you don't merge to the backbone curve, but you merge something below. It just depends on what you want to do with your model. Maybe not that important, but the pinching, it is important.
Yeah, no, what I say in fact is that when you look at it without testing it, it looks like just, okay, yes, it looks like a better hysteresis loop, but it's not so important. Instead, it is it's very important, because when you do, from what I've seen actually, the more cycles you do, the more important it is, because otherwise you accumulate too much damage. Because in the real case, basically, when I have pinching, I start damaging when I reach the other point, the previous point. In my case, I will start damaging here much before. So basically, it's like I'm stressing my structure more and more if I do not recover all the plastic deformation. Now, the bad news is that in three-dimensional models, it is not easy to implement this thing. Okay, so in 1D models, it's easy because it's easy. I mean, from a computational point of view, it's easy to keep in mind what is my last stress point, and I'm reloading here. It's like a 2D graph. In a three-dimensional model, is quite difficult. We have some ideas now, recalling the concept of microplanes, which actually converts a three-dimensional model into a series of vectorial models. So we have some ideas, and we are working on it. Because
Massimo, going back to what you said before, in your constitutive model for concrete, have you checked how are you able to capture this coupling that Jose was talking about between the compressive strength and the cracking in the orthogonal direction?
Yeah, I was going to this other point actually. So one problem that with homogeneous model you have is that it's from a computational point of view. Actually, it's very difficult to implement a non-linear unloading reloading function. Okay, which is easy to implement in 1D, is not so easy to implement in 3D. There are ways, I'm testing them, but it's not actually a pure, you need to convert a tensorial model to somehow a series of interfaces. With the concept of microplanes, for example. I don't know if you have heard about the microplane theory with Bazin, but the concept is pretty similar. So I will test this material model in that direction. So that is one problem. Okay, so the hysteresis loop. And the other problem, I think, which is the one that you are mentioning, is the homogeneity that we have, because in our case it is an homogeneous material, an isotropic material. Okay, and I'm not talking about isotropy in the elasticity. I'm talking about the isotropy of damage. On the other hand, in the beam thrust model, there is coupling, but not completely. But correct me if I'm wrong, Professor Restrepo. For example, one example. One thing that I've said to Professor Conte is that imagine you have a certain real behavior. What you have to expect from isotropic material models is that you are somehow on the lower bound, and with either the beam thrust model or the concept of fixed cracking models also, you are somehow on the upper bound. My idea was this one, but correct me if I'm wrong. Let's see what happens, for example, in isotropic constitutive models. Okay, so imagine this is my yield surface in plane stress conditions. Okay, something like this. Now imagine my element, which can be this element here. Okay, so in a first cycle, it is being subjected to a vertical deformation. Okay, so I will start from here. I will hit my surface at this point. Okay, then my surface will shrink according to the an exponential softening, and let's say I go up to this point. Okay, so with this exponential softening, even if I'm hitting the surface orthogonal to this crack, what I'm doing is that I'm shrinking the entire surface. Okay, so what happens is that, so this is my new surface basically. Imagine that on the next cycle, this one closes, I will load it in compression, then I will do another cycle, and this one will open, this one will be subjected to compression and shear. When I will hit the shear surface, it will be hit much before, because it has been damaged in tension before. So damaging an element in pure tension actually shrinks the entire surface. Also, the shear strength becomes much smaller. Now, somehow it can be also real, but in our case, it probably is way too much, because imagine an element that is completely cracked in tension like this. Then I apply shear. It may happen that it slides instead of creating a diagonal crack. Okay, so it makes sense that the global shear strength is a little bit slower. It's a bit lower, but in our case, it seems like it is damaged too much. Now, on the opposite, what I see from either the truss model or the fixed models in general is that it is the opposite, basically. That's why I say it is on the upper bound. If I imagine a representative element from the beam truss model, something like this. Now imagine this one is subjected to uniaxial tension in the vertical direction. What I will see is that this element will deform like this. So the two elements here will experience damage in tension. But the two diagonal elements, they are perfectly virgin. They do not have any problem, because in this case they are both in tension. So when I unload and reload on the other side, yes, I have damage here, but these two are perfectly undamaged. So now what is the real behavior? Let's say something in between. So that's why I was saying, when you use an homogeneous model, you should expect that you damage a little bit before the reality, because actually I'm spreading the damage all the directions. If I have a certain crack, it's like my material model is cracked in every direction. Okay. So
yeah, I think if you have a large tensile strain, you will not affect the compressive stress-strain relationship unless you have high shear stresses in that region as well. So what we have done here is that we have totally uncoupled it. No, the tension has no effect whatever in the compressive stress-strain relationship.
In fact, exactly. So that's why I think probably you will be a little bit on the upper bound. In our case, you are a lot on the lower bound because of one reason. Even if you have, for example, if you have a lot of compression, but then you load it in shear. When you're loading in shear, at least one of the principal strain is positive, and then the other is negative.
Right.
So
right.
Imagine you have completely damaged the tensile surface. So this one is my original surface, which was something like this, and this one the compressive one. Imagine I completely damaged the FE, so in such a way that it goes to 0. Okay, so this one is my residual surface. Whatever I have here, even if the compression is
right. Yeah.
I'm always outside the yield surface. That is
exactly
that we have with isotropic models. That is a huge problem. That is because typically in isotropic models you cannot have something like a surface something like this that is completely damaging tension, but has a residual shear when you have some compression.
Yeah.
What we are trying to do actually is to work on these little aspects that can make the response more realistic, because there are these small aspects that probably are not important when you're trying to do a monotonic test, but they become a lot important when you do cyclic tests. Because people often do not look at them because they do not seem very important. But when you start doing, I've seen exactly with this example, when you do a lot of cycles, it's a mess if you don't get these points. So this is something we are planning to work on. But this is actually general of any constitutive, any tensorial model. In fact, one of the reasons why, for example, Bazan decided to go with the microplane was that a real homogeneous model cannot be applied actually to concrete or any other disordered material. It can only be applied to metals, like material. But of course, we want to use them also with concrete-like material models. So yes, there is some work to do in the three-dimensional approach. But yeah, the topic was what we have said with Professor Restrepo last time. So there is not a unique model that can work for.
No, and there will never be the perfect model. So let's go to steel. Steel will work at the macro level. And if you want to go all the way to the grain size, you see all kind of problems as well, inclusions and defects and all these things that are really challenging to model. So we, at some point, you stop your magnifying glass and you have some empirical parameters, and that's fine.
Yeah, sure.
Because we need to provide the way I see the problem is that whether we stand on the material science of things or whether we want to offer something for the community to solve a problem.
Exactly. Yeah, I think one of the reasons we made this webinar is to have to show what you have in OpenSees. You have many tools. Not all of them are perfect in every situation, so it depends really on what you are trying to achieve. So yes, just to show people, for example, the cyclic behavior of the truss model, because Professor Conte was, I don't know if you try to run it, but if you run the one that I shared last time here, which is the cyclic 03 CTM cyclic, you should be able to see something like this. So this one will be the output of the monitor. Okay, now in this case, probably it's much more pinched because in this example, I didn't use the Menegotto pinch, I was using the hysteretic model, and it has a more peak-oriented behavior. But the point is that being able to recover the plastic deformation and load back to this point, here you start accumulating extra damage. While in tensorial models, you will start accumulating this extra damage much before because of the shift of the plastic deformation. So the cyclic behavior is something which can be quite important if you are planning to, if you think your model will be subject to this kind of loads.
Massimo, when you talk about tensorial model, sorry, Jose, you talk about most general three-dimensional stress strain.
Any general three-dimensional model, basically, even if, well, there are many kind of model, plasticity-based, damage-based, but at the end of the day, what they do is that they take the stress tensor and with a function, which is the yield surface or the damage surface, they convert this tensor into an equivalent scalar. And with this equivalent scalar, they do govern everything. That's why they behave as a very homogeneous and isotropic material, because at the end of the day, you have just one scalar measure. Now, in our case, it is a two-parameter model. You have two scalar measures, one for tension and one for compression, but you do not distinguish different directions. Now, the problem with the hysteresis loop is that when you are I'm talking about a programming point of view, not a theoretical point of view, because in theory you can do anything you want, but from a programming point of view, it's easy in a 1D model to keep in mind, okay, my last point on the positive side was this one, then I unload it, I'm here, now I'm unloading, I'm pointing toward this point. I can easily define a function that brings me to this point, but it is not the same if I'm working with a surface. Now imagine I have the three-dimensional surface of concrete, which is something like a cone in 3D. Now it's a little bit complicated to model around the hydrostatic axis. Imagine I hit the surface at the beginning here. And then I'm unloading and I'm here. What is the next point? It is this one, but probably I will load in another direction and I will go here. So it's not so easy to define what is the non-linear unloading path to reach the other point, because the other point is not in a fixed direction. Instead, in a uniaxial model, you are in a fixed direction. So that's why it's a little bit easier to implement a non-linear loading and unloading rule. But actually, it's very important because what we have seen, for example, if you want to keep this kind of unloading stiffness with a tensorial model, this point here will be hidden at this point. And when you will reach here, you will see your structure completely damaged. So that's why.
I mean, sometimes you use a plane stress, right? Constitutive model for concrete. So when you say tensorial, this is to distinguish with the plane stress modeling of each layer of a shell, or?
No. When I talk about tensorial, also a plane stress model can be a tensorial model. I mean, okay. It's not either a scalar model like a uniaxial model or a vectorial model like the microplane model. They work with tensors, not with scalars or vectors, which is a little bit more difficult. And since you treat the entire stress tensor as an equivalent scalar, and you work in the principal direction, it means that you are not caring about the direction of the stress, okay, the direction of the action. That's why when I say if it is damaged in one cycle, in the other cycle, even if the loading direction is different, the material model will be completely damaged because it works in principle, in the principal stress space. So you do not take care about the damage induced anisotropy, which is something that we want to put also in the model.
Yeah, I understand. Yeah.
So there are drawbacks, as we said, there are nice things and bad things from both points, because with a three-dimensional model, you are able to have the biaxial increase in compression, the triaxial behavior, but you have also drawbacks. You cannot model things like this kind of unloading, reloading function. So each model has advantages and disadvantages. This is the point. No model is completely perfect.
I'm not aware of any benchmark problems where you could calibrate completely a plasticity model like this under all kind of loading generic loading situations or so. But I think those are important that somebody working in this area and young, all like us, begins to develop.
Can you move? I think there is someone that should be muted. Okay. Sorry, Professor Restrepo, we'll try to mute. Guido, can you mute?
They need to maybe, and this is an opportunity for people like Nicola also to start assembling a team of people around the world to work on a series of benchmark problems, experimental and numerical problems to solve the next frontier. I think that's important.
Yeah, sure.
He's working with me on masonry. I think in concrete it's important too.
For sure, it is important because often people rely on one model that can solve everything. But then, I mean, when you try to model this complex behavior, you should be aware that this kind of analysis is not something that you can do and trust the first time. You need to pay attention. You need to pay attention to the model you select. If it matches the assumption, what you want to simulate. So yeah, you have to be careful when you do this kind of analysis. So the idea of these webinars was to show all the tools that you have in OpenSees, their advantages and disadvantages, so you can use them, let's say, correctly as much as you can. Yeah, these basically were the points that I wanted to highlight from all the lessons that we have done. Now, I don't know if you have any questions, because I think Professor Restrepo, I think you are already late, but so if someone has questions for Professor Restrepo, please.
I want to add a point. It will be good to have a series of benchmark problems like this one, and find all the problems around the world, do a little bit of a database, and some of them you show the various solutions, and other ones you leave them as exercises for people to solve. So
yeah, actually, in fact, Guido, you remember, Professor Restrepo, if you've seen on our website, we started creating the verification manual for OpenSees, which is general. We wanted to do something similar for reinforced concrete structures, collecting a lot of experimental tests and try to see what model in OpenSees you can use to model that. So it would be nice to set up.
Would be very interesting to have a joint effort, like to find the University of San Diego and other university. We can definitely join together and do that. It would be very, very interesting. Also for
we can't guarantee good weather, of course. And the other things that we're working here, again, on 1D problems mainly, rate-dependent materials for steel. I think that's a hidden topic, and I think from the shaking table test we have done in the past, I think the rate dependency of steel actually can account for much of the damping you need to put at the front end in the analysis. So if your reinforcing steel is rate dependent, you should be able to reduce your damping quite a bit. The rate dependency of concrete, it's not as important because the strain rates in concrete are much lower if the neutral axis depth moves towards one side. But those in steel can reach 10-20% per second, and those are not negligible at all.
Yeah, in fact, what I've seen is that in steel models in OpenSees do not use this concept of the implementation in OpenSees. We have one in OpenSees, but it's not public yet. Until we publish, we are writing a paper, and though the paper will be, hopefully in a year it's published, and then the model will be made available to the general public. Actually, in the concrete model we have the viscosity, so you can play a little bit with rate dependency, but with the simple Perisna model. So I don't know if you had something better in mind for steel, but yeah, that would be nice also.
I have to go, and I'm sorry, I have to go to a medical appointment, but it's nice, and thank you for organizing and inviting us here.
Thank you, Professor, for being here on the last lessons and this roundtable. So once again,
thank you for joining, also from me.
Thank you. Yeah, thanks.
Thank you.
Okay, so I don't know if anyone has questions, if you have tried the examples that we shared. We still have some time to answer some questions.
I have one question, Dr. Massimo. So I have a model. I used ASDEA shell element and damage TC3D for the concrete. And say like my original time step, like cyclic test, for example, like if it's like 100 time steps and it converges, and right now if I double it, and it's very strange for me to see that it does not converge after several displacement cycle for this one. Do you have for this example?
If you decrease the time step?
No, increase the time step, like double. Like for example, previously is 100 time steps. Now I increase it to 200.
Okay, so you are decreasing the time step. I mean, you are increasing the number of increments, so you are decreasing the time step. Okay. Now, typically, when you have nonlinear models, you think that with a smaller time step you should converge, but sometimes it may happen that with a large time step you overcome. You can actually pass a non-convergence point just because you are jumping over it. Now imagine you have a very unstable point here, like you have a sort of snapback, and then it goes here. Sometimes when you use a large time step, you can directly jump to this point. It's very rare, but sometimes it can happen. Okay, so it's not so strange to find this kind of behavior. It doesn't happen very often. But the problem when you have softening sometimes is that, yeah, you have many instabilities, and sometimes using a large time step can help you jump. But the problem is that it is unpredictable. You cannot say, okay, I make the time step a little bit larger, because then it can deteriorate the convergence somewhere else.
Oh, okay. Because
is it related? Yeah, sorry, Lynn, go ahead.
Oh, because in my opinion, so previously you were dangerous by bifurcation, so that's why I want to you know, increase the time steps to see what's going on, whether in my problem there's a this kind of issue. So that's why
if it is monotonic, you can try to use the arc length method. Sometimes it works for passing this. Then the problem that you have with the arc length method is that it will be a mess if you want to do the cyclic pushover. But if, for example, instead of applying an imposed displacement, you can impose a force and try to use one of the, there are new, or let me show you what is the one that, in my opinion, was working better in OpenSees, and you can try, is the, imagine this one, okay? Imagine you set up an analysis in a displacement control fashion, okay? Like when you use displacement control, so you apply a force and use this one. Now, instead of using displacement control, you can use arc length. Now, there are three kinds of arc length in OpenSees. This one was the very old implementation, and I've seen the AQ path is slightly better, because I've seen with this type of, I'm not extremely experienced about the implementation of the arc length in this new class here, but I've seen that the minimal residual displacement works quite well when you have instabilities due to strain softening. Because actually one problem that you have with the arc length is that it works good for elastic instabilities like in buckling, because typically when you have instability snapback due to buckling, you only have a let's say an elastic structure, but with large deformation it goes in buckling. So basically, I don't know why it's canceling the drawing. Yeah, sometimes what happens is that, oh, Guido, I don't know why. I try to draw and then it disappears. Okay, well, I don't know. I was trying to do, I will try from here. Let me see if I can do a notation here. So if you, oh, because I had to clear all drawings, sorry. Okay, let me try again. So if you snap back due to buckling, no, it's not like this. I don't know why. Let me try again. Oh, the drawing is here. It's only disappearing on my.
Yeah, we can see it. We can see it.
Okay, perfect.
The snap through and snap back, right? Combined.
So exactly, the arc length works on the concept of, imagine you are here, you are searching around this incremental arc length. You typically have a couple of solutions. One of them is the loading path, because it is going in the loading direction. The other is the previous path. Okay, so you typically discard this point and you go in this way. But when the instability is due to softening, you have something different. You have something like this, okay? And then when you are up to here, you have three possibilities: going back to the previous path, loading on the loading path, or going back to the secant unloading. That's why you have this third one that typically, if this one is closer to the loading path, sometimes the arc length can confuse the loading path with the secant unloading. But what I've seen is that
but you even have one more, right, Massimo?
Yeah.
One is if you continue to load monotonically. Right? So
yeah, 3. That's why I said 3. You have the previous part. So if you go back to the like if you have an elastic nonlinear material, then you have the loading path, but then you have also the unloading, okay, which is the one that you don't want to capture. The problem is that if you use the cylindrical arc length, the standard one, it basically makes the assumption of choosing the direction which is, let's say, the most opposite to the previous loaded path. And sometimes the unloading and the loading path in a damaged model, they are pretty close at the beginning. Now, I don't know so much about the theory about this new one, but what I've seen is that the middle residual displacement works pretty well. So it is worth to give it a try if you want.
So it's a solution strategy that
just
is not displacement
kind of
control, that is not arc length, is something else, right?
It is a particular arc length. Let's say.
Oh, it's a particular arc length. I see.
It's always called arc length because the concept is the same, but the way you select what is the next point is different.
Sure, because arc length, like you said, right? If you have an equilibrium branch that comes from, especially like you said, buckling, but even inelastic buckling, right? You have one very nonlinear branch where you can have snap through and snap back and you can follow it. But now what about if you do cyclic loading, you know, like hysteresis loops? I think the arc length, when you do the unloading, it could be confused and get the other solution that goes in, that continues to load, right? It's not obvious.
Exactly. That's why I said to Lin soon, if you are doing a monotonic test, you can try to use the arc length. If you have this problem in a cyclic test, then it is a mess, because basically what you have to do is to first do an arc length to reach this point. Okay, so you can capture these light instabilities and you reach to this point. Then you do a standard load path, a standard load control until you cannot go on anymore, and then you switch to arc length. But it is really a mess. That's why I said test it if you can do it with a monotonic test. But for cyclic loading, it can be done, but it's not so easy to program. Okay.
Okay. Thank you.
And then Massimo, one question here about Lin's question is, it could also be related to what we were discussing, right? The bifurcation problem where you could have many equilibrium branches, and then if you use a large load step, like you skip over this complexity, you know, by chance, I would say in some cases. And
sometimes you pick a wrong path that you may not want. This is one of the main problems that you have with softening.
Yeah.
I think we have a couple of more questions. Some comments from Nicola Tatke. Yeah, sure. Okay, so he was commenting about the unloading and loading. Yeah. So you had the same problem with the concrete damage plasticity in Abacus, right, Nicola?
Yes, Massimo. Yes.
Okay. And then we have a question from Gustavo. Some of these methods or models can capture the failure modes of walls as rebar fracture or out of plane, or maybe which is the best method to model it. Now, this is one of the cases in which you may need the three-dimensional model. Why? Because the cyclic truss model, it is made for the in-plane behavior. Now, if you remember Professor Restrepo, when he gave his speech, he said that they extended the version that I showed you, so the pure two-dimensional version, in a three-dimensional one, which is the beam truss element, in such a way that you can model them in a three-dimensional environment, but they are not made to perfectly capture the out-of-plane failure. So they use beam basically instead of trusses for the horizontal and vertical lines. But just to give an out-of-plane stiffness so that you can place shear walls in a three-dimensional model. Now, the point is that if you want to model out-of-plane behavior, you need to use a shell model, at least, if you don't want to go with three-dimensional models. And then you have two options. You can either use plane stress material, like the first one that you have seen. Let me go back to first one was shell smear. In this case, I was using the plane stress user material. Now, this one is a plane stress material, which is pretty similar in the shape of the yield surface to the one that we have, the three-dimensional one. The point is that this one is plane stress, okay? It is still fine. It means that if I do a drawing here, imagine you have a shell like this. Then at each Gauss point, you have many through the thickness integration point, okay? And in each integration point, you have a plane stress, state of stress, okay? So basically, you don't have out-of-plane shear. But for bending, it's fine enough, because basically, even if you have only plane stress at each point, you can represent bending, of course. What you cannot represent is a nonlinear transverse shear, but you are only interested in that if you have very thick plates, which I don't think is the case for the typical case in reinforced concrete, or if you want to model, for example, punching shear. Of course, if you want to model punching shear, you need a model that can capture nonlinear transverse shear. Now, in that case, you may want to use a three-dimensional model like this one, okay? And I also talked about this. If you want more details about the difference between a plane stress material and a full 3D material with respect to transverse shears in shell, you may want to look at the webinar about the out-of-plane failure of masonry. Okay, there I also explained why it was so important to model out-of-plane shear. Okay, so yes, you can capture somehow the out-of-plane failure, but it depends on the model that you choose. Okay, so yes. Please, can you speak a little bit of rocking? Which consideration is necessary for model this type of connection? Well, so I mean, rocking can generate naturally if you want to model, if you want to use three-dimensional models, and in reality you have rocking because of the develop of flexural cracks at the bottom. It can naturally be represented by three-dimensional model, but then you talk about connections. So you want to model them as a lump, let's say as a lump nonlinearity. I do not understand how you want to model them, because if you want to actually model rocking, like, okay, I already have a crack which is fully open and I want to model it as a lump plasticity, then it's simply like basically like contact. It depends on how you want to model it. Can you elaborate a little bit on it? Hello, Jonathan? Just the contact. Okay, well, basically, it depends on what kind of model that you want to use. For example, you are modeling just beam elements, it's a nonlinear rotational spring. If you want to model three-dimensional elements, of, let's say like shells, okay, so you basically have this wall here, and you want to represent rocking here at the base with another object, then you need to use the contact element that you have in OpenSees. Now, contact can be only lateral contact, which for rocking is enough. Otherwise, you can have frictional contact if you want friction. And we gave a webinar. So if you are interested in modeling contact, you can go. Let me point you to the right webinar. and then STKO OpenSees, STKO Academy. You go on e-learning courses, and then down here you have explicit contact element applied example. No, not this one. Sorry, the new element. Let me find the contact. No, it was this one. Yes, soil foundation interaction and RC structure. Yeah, here I was talking about the new contact element that we added in OpenSees. Okay, so you can have a look at the webinar 24 if you're interested in the contact thing. Okay.
And Massimo, there is also an interesting now tutorial webinar of Jose Abel regarding the DRM. So maybe you can also suggest.
Yeah, just the new webinar, the next webinar.
No, but also Jose gave already a webinar, so maybe they can look into it. It's very interesting.
Yes, I don't have the link now, but I think it's very close on LinkedIn.
He's in LinkedIn correctly, and he's in his website. So his website of Jose Abel. Maybe you can just look Jose Abel website and you can get the link. I think it's a very interesting thing to look at.
Oh, it is here actually. Here there is a link to the.
Yeah, and then you look at the here it is.
You can look at this. This one is a new implementation that we have here. Well, it's not about contact, it's DRM, it's another thing for modeling soil structure interaction, but this one will be the topic, hopefully, of the next webinar. We have to talk with Jose Abel for the next webinar, but it is a new way for modeling soil structure interaction. So yes, you can have a look at it.
Especially dissipation and reducing the volume of the soil that you need to consider. So it's very, very interesting.
Let me go back to the questions. Okay. I don't know if is there any other question? Meantime, I stop sharing. Okay, so if there is no other question, I want to thank you for being present in this webinar series, and yeah, so thank you, and we will see you in the next webinar. We will let you know what will be the next topic, but hopefully it will be the DRM, so which is basically a new approach for imposing the, let's say, the earthquake loading on the soil domain. Okay, it's a new tool implemented by Professor Jose Abel, and we also have the tools for using this input inside STKO. Okay.
And Massimo, maybe you should mention about the Python API. Like that's a very interesting course.
Oh yes, in October. Then that will be in October. We are planning to do another. Well, actually, it will be a class series for explaining how to use the Python API in STKO. It will be a series of webinars, and we will give some examples, mainly on optimization. So how to write Python scripts inside STKO to start with an initial structure, automatically do an analysis, get the results, then do some operation on the results and change the input and do it again and again. For example, what happens with optimization or model updating or any kind of this kind of approach where you need to talk between the preprocessor, the processor, and the post-processor. Okay, it will be in October, but anyway, we will send a newsletter to everyone. Okay,
it will be 8 hours. Maybe you should say that it's going to be only invitation only for people that are able to use Python, and only
sure, that
are going to attend.
Yeah,
sure. It's not a normal webinar.
Yeah. Okay, so thank you everyone, and see you in the next webinars. Bye.
Thank you. Bye.
Bye. Thank you.
Bye, Joel. See you soon.
Yes.
I think
Yes.
Rico fell asleep, didn't say anything.
No, no, I'm here. I wanted to say, actually, Joel, reply to my email, please.
Yes, I just did, Enrico.
See you
How are you
soon.
doing?
Ciao. Thank you.
Bye. Thank you.
Bye.
Bye.